What I'm going to attempt to do here is to demonstrate some of the features and functionality of the pseudo-OS programming methodology. In the introduction to pseudo-OS, this would be project number 5. Basically, it is trying to take all the functionality that would normally be required of a real-time operating system and throwing everything but the kitchen sink at this microprocessor and showing that you can actually perform the multitasking real-time operating system functions at the application level if you have the proper design methodology. So this is a completely new approach to programming. Personally, I've been involved with embedded programming now for probably over 30 years, and haven't seen anything quite like this in the past, and it's a combination of quite a few hardware and software design methodologies. So let's just start out here by pressing the button here. You'll see that just basically waking the system up. What you're seeing here with the LEDs is a simulation of real-time processes. Now this is kind of the benchmark. We never want to see these LEDs disturbed in any ways. So basically what they're doing right now is they're going through 4 completely different states, and it's also under the control of this potentiometer here. So as I change the setting of the potentiometer, it changes the speed of the LEDs or the count rate. Now what it just did was it went to sleep as it is programmed to do after 30 seconds. So let me wake it back up here. So now it's running, and you can see the effects of the potentiometer of slowing down and speeding up the count rate and the scan rate of the different states that it's going through. So it's going through 4 different states. It changes states every 5 seconds. Also, when it's flashing and counting, it's also, you might not be able to see it, but it's also cycling at 33 hertz. So there's a very fast pulse rate behind some of these displays, and again, that would represent a different task in a multitasking operating system that would be basically assigned the task of just flashing at 30 hertz behind the other function that's doing the counting or the scanning. So over here we have a little bit of a hard time because of the glare, but essentially what we're doing here is we have a clock. As you can see, it's got the day of the week and the time, and it's counting 1 second. It updates every second. This is going on, again, as a separate set of functions. I won't call them tasks. In this environment, we call them action objects. They're basically running in parallel with this other functionality here. And basically what I did was just press the first button here, and I went into a menu. So the menu will stay alive for 10 seconds, and if there's no activity, it will revert back to the main menu. So I'm going to press the left button again, and the left button is basically a select. So we can review, we can upload, initialize a database, or set the time. If I press it one more time, it's going to step out of this menu and go back to the main menu. Now, out of the corner of your eye there, you might have noticed that there's absolutely no change at all, regardless of what we do with the display, with the high priority functions represented by the LEDs over here. Now, one of the things that I've done here is I've set up a logging system that 287 means 287 records have been logged. Every hour it's logging the temperature. So right now it's 68 degrees here, and the high that it's seen since it started was 73, and the low's been 54. So what we can do here is we can go into the review menu, and if I select with the right button, if I select review, this is basically the first record, and we can step through the records like this, and for every hour of the day we can see what the temperature was. And again, this is just a simulation, and again, you see no changes at all in the LED patterns here. They just go merrily along their way, representing some high priority function in a factory or an automobile or something like that, so where the user interface is not affecting the critical tasks that are running at high priority. 10 seconds no action, it's gone back to the main menu. I'm going to select again the other menu we have up here. The second item that I've selected is called Upload. It's going to basically upload all of its reports through this RS-232 connector to an X terminal or whatever we want, but right now it's just going to basically blast it out the RS-232 port. There'll be nothing there, but it's still going to upload. So essentially what we'll do is we'll select Upload again. I'm going to press the Enter button, and you can see that it's uploading the records. You can see the count going. Now it's finished. So it uploaded 287 records. Let's go through this process again, this time looking at the LEDs to try to detect any slight variation at all in their pattern while we're uploading. So ready to upload here. We're going to go over here, look at the LEDs, and now we're uploading. You can see the count off to the right, and there's absolutely no change at all. So essentially what I've tried to do with this demo is throw everything that I could possibly throw at this microprocessor that would represent a real-time operating system, and you can see absolutely no change whatsoever in the behavior of the response to real-time events, and it continues to keep accurate time regardless of what the other user interface issues are going on. So essentially I could put probably another 10 or 20 tasks running on this thing, but I think I've probably got about 15 tasks right now running, what equivalent of tasks. They're not really tasks. But the pseudo-OS, the pseudo operating system, actually allows you to program an embedded functionality or an application where you would typically need a real-time operating system that allows you to do it using some state machine methodologies and whatnot without the real-time operating system kernel. And you can therefore put very sophisticated applications on a very, very small footprint. This is a very exciting methodology that we're working on right now. I'm currently working with a PhD professor at a local university, and we hope to get this at some point in the future into book format and get it out on the market so that people can benefit from this methodology. Again, after 30 years of embedded programming, I've personally never seen anything like this, and I've usually paid pretty close attention to things that come across my desk in terms of methodologies. This methodology is derived from artificial neural networks and some hardware design techniques combined. So it's kind of unusual to combine those particular philosophies, but it works like a perfect charm. So I hope that you enjoyed this little demo, and I hope that you keep an eye out in the future for more information regarding pseudo-OS, and hopefully one of these days we'll be able to get a book or a technical manual out that explains the details on how you set up the state machines in order to do this. By the way, this methodology is extremely easy and intuitive to write code for, and it just uses straight ANSI C, and it is also very, very easy to maintain because everything is in the tabular and list form, and the states are changed almost instantaneously, and very, very good response time, very low overhead. So, I hope you enjoyed it. Have yourself a good day. Take care now.